Hello, my name is Christina Taylor. I'm a PhD student in computational and applied mathematics at Rice. The work for this project was the result of my internship last summer with the Numerical Algorithms Group in BP's Center for High Performance Computing. In the abstract for this talk, the performance of the code developed is briefly mentioned. In this presentation, we'll go over some of the considerations that allowed that performance to be achieved. First off, this code uses concurrency via CUDA streams, which is a secondary layer of parallelism. Where there's parallelism, we need to be mindful of data dependencies. In our setup, we have two layers, the taper layer and the one-way layer, that constitute our absorbing boundary condition. With concurrency, we can apply the absorbing boundary condition faster by splitting each of these layers into one kernel per boundary. While this can be done without issue in the one-way layer, we have to be more careful with the taper layer due to the overlapping data dependencies. Just as we need to be mindful of data dependencies, we also need to consider hardware usage. Two very different methods for processing the boundary layers were implemented, and unintuitively, these kernels resulted in basically the exact same runtime on the test domains. Deciding which one to use required evaluating their robustness and scalability to ensure a code that would perform well on both test domains and production datasets and different GPU setups. While the past 2 points occurred on single GPUs, there was also the issue of cross-GPU communication. Typically, one would assume less computation results in a faster code. If we compute the absorbing boundary condition before the halo exchange, we do not have to calculate the absorbing boundary condition in the receive regions. However, the absorbing boundary condition must be computed after the finite difference update has completed in the entire domain, or a race condition will occur. The absorbing boundary condition kernels do not take enough time to hide the halo exchange, so synchronizing before the halo exchange to fix the race condition is actually drastically slower than synchronizing after the halo exchange, despite the second setup requiring us to process the receive regions. Before wrapping up, I would like to thank the Numerical Algorithms Group and BP yet again for hosting my internship, and give special thanks to my advisor on this project, Mu Hong, for her constant support and guidance. Thank you for your time. This concludes my talk.